Good afternoon, everyone. Welcome to another lunchtime seminar series. Today, we have the pleasure of hosting Dr. Andrew Telford from Imperial College London. Andrew is a material chemist with solid experience in the design and fabrication of polymeric and inorganic micro and nano architectures. He did his BSc chemistry at the University of Siena in Italy in 2004 and his MSc in University of Florence, Italy in 2007. Currently, he is a junior research fellow at the Department of Physics, Imperial College London. And his current work involves development of new thin film solar cells and light-emitting diodes, primarily for solution-based processes. So today his talk will be on advanced optoelectronic tools to interrogate solution process solar cells with the focus on polymer fullerene bulk heterojunction solar cells and also the hot topic of hybrid organic lead halide perovskite solar cells. And since we have both strands of work happening at UNSW, I hope there will be a lot of interest from the audience. So without further ado, let's all join in welcoming.
Thank you very much. Thank you for the introduction, and thank you for taking the time to come over. As Supriya said, I'm a junior research fellow at Imperial College, and I'm hosted in Jenny Nelson's group, who's this person here, in the Department of Physics. Now, I started as a chemist that was working on biological interfaces with polymer thin films, so this was really quite new to me. But it's been very interesting. So I've been working on a bunch of optoelectronic devices, particularly for solar applications, and trying to develop optoelectronic techniques to try to understand the mechanisms behind some of the behaviors. So my work focuses mainly on materials that can be printed. So obviously you have your organic bulk heterojunctions, you have your lead halide perovskites, but also I've been working in collaboration with a bunch of people in Valencia in Spain on these doped graphene that they make from bio-waste, so chitosan and alginate, to make both electron acceptors in bulk heterojunction, but also ideally transparent electrodes. And also I've been involved in work with where we try to make hybrid solar cells in blending inorganic quantum dots with conjugated polymers to make solar cells. But today I'm going to focus on the perovskite work and on the organic bulk heterojunction work. And in the future, ideally, I would like to bring together this research avenue of thin films organics with what I've done interfacing biological material, particularly cells, with surfaces. And the idea is to understand something about the communication between living cells and an abiotic electrode. Right? And this has all sorts of interesting applications, one of which in photovoltaics. So you could get cyanobacteria, so bacteria that can absorb light and produce electrons at a certain electrochemical potential. And then by carefully designing the interface between the bacterium and the electrode, extract those electrons to do work. But for now, I'll stick to the perovskites and organics. And the first part would be on trying to understand the mechanism behind hysteresis in some of the lead halide perovskite solar cells. Now, I'm sure you're familiar with the phenomenon, but basically some of the architectures of these perovskite solar cells exhibit a sharp difference in the current voltage scans when you scan towards forward biases or towards reverse biases. Right? And the difference between the curves is referred to as hysteresis. And when I say perovskites, I'm going to focus specifically on methyl ammonium lead triiodide perovskites. Okay, there's a bunch of mixed materials out there, but this is kind of the main, the simplest one that can be studied. And you can see that it has a structure where you have a lot of ions. Okay, lots of ionic stuff. You have iodide, you have lead in the middle of this octahedra, and then you have your methyl ammonium trapped in these voids, in these cages. Okay, so it's not surprising that one of the ways to explain this peculiar electrical behavior, this hysteresis, has been the presence of ions that are able to migrate within the bulk of the material. All right? And it's even less surprising if you consider that this is a solution process material, so it may be non-stoichiometric, so you could have excess ions or a defect of ions, so charged ionic vacancies that can be affected by electric fields. And one way to try to understand the effect of mobile ions in the solar cells is to imagine that you have your bulk material here in yellow, and you have anode and cathode. I'll keep this color coding throughout the talk. So if you imagine that you're scanning from forward biases, so towards reverse biases, the polarities of your contacts will be like so. And if you have ions that are able to migrate within the bulk of the material, what would happen is that they would be able to accumulate at the interfaces between the active material and the electrodes, okay, or the hole and electron extraction layers. And by doing so, they would create an electrostatic potential that, in this case, aligns with the intrinsic electrostatic potential of the cell, which is given by the different work functions of the electrodes. Okay. Now, if you scan, and I'll get back to that later, if you scan from reverse biases towards forward biases, you can imagine that the situation is reversed, right? So now the electrostatic potential, the electrical field that is formed by accumulation of ions at the interfaces points against the intrinsic electrostatic field of the cell. So you can imagine that that can affect the performances. Now, one of the ways to try to break down this problem in simpler pieces is to forget about current voltage scans, which have the additional variable of scan rate, which can affect the hysteresis, and just look at the voltage. Okay? So what we do in these measurements is to keep the cell at short circuit in the dark for a certain length of time, and then at time 0 here we switch the cell to open circuit under a white light illumination. All right? So for a conventional solar cell, if you want, you would expect the voltage to very quickly drop down to its steady state VOC. Okay? But in materials, in devices that exhibit hysteresis, this doesn't happen. In fact, you see a relaxation of the VOC towards a steady state value, which can take up to a minute or two. Okay, so it's quite slow. In the in the same way, if you precondition the cell at short circuit, so now you're at 0 volts, and you switch the cell to open circuit in the light, again you have this slow evolution of the VOC, but instead of going from higher values to a steady state, it comes from lower values and get to pretty much the same steady state value. Again, in about a minute. So there's a slow process happening in these devices. We're pretty sure that it's due to ions accumulating at the interfaces and then rediffusing back. Okay, so the diffusion of ions is what controls this lag in the response of the cell. And the way we came up to understand it is by tweaking with transient photovoltaic spectroscopy, and in order to be able to look at this problem from 2 different timescales. Okay, so you have your slow evolution of the voltage after preconditioning in the dark at short circuit, which is this blue curve here, and that can last up to a minute, so that would be your slow transient, and then on top of that, every second we will use a pulsed laser to collect a snapshot of the electrostatic potential, if you want. And that is by simply looking at the transient photovoltage. All right? So I designed and built the rig for this particular application, which was good fun. It was my first experience with electronics, really. And the interesting bit about this rig is mainly the laser. So instead of a conventional pulsed laser, we use continuous wave lasers that can be switched on and off very quickly. So that means that we're not limited in the width of the pulse, and you'll see that having a longer pulse in this case is beneficial. All right, so let's look at a device which typically exhibits hysteresis in the JV scans. All right, and this is a device that we refer to as bottom cathode, just because we're extracting electrons from the glass side, from a titanium electron extraction layer. Then we have the methyl ammonium lead triiodide, spirometad, and gold. So on the right here, you'll see what happens at time 0 after we've kept the cell at short circuit in the dark for a minute. And at time 0, we switch on the white light and switch the cell to open circuit. Okay? So you see that there's this slow evolution of the VOC. And then on the bottom down here, you'll see a video that shows transient photovoltage spectra collected every second. Okay? And I want you to focus on the shape of these curves. So what you're seeing is that as the voltage is relaxing to some sort of steady state value, the response, the transient response of the voltage is changing dramatically. Okay? And in particular, you have a negative transient photovoltage for the duration of the pulsed laser, of the pulse of the laser, which is 500 nanoseconds here in gray. And that negative transient photovoltage recovers, so disappears as the VOC recovers. Okay? Now, the only way to have a negative transient photovoltage is to have a reverse electric field inside of the device. And again, going back to this accumulation of ions. Okay? By reverse, I mean pointing the opposite direction compared to the intrinsic electric field of the device. And the way we think it works is like so. So you start at short circuit, so your cell is in the dark at short circuit, and you have your usual sloped band structure that you expect from the asymmetry in the contacts. Okay? Now, this means that you have an internal electric field in the device that is pointing towards the left of the slide. Now, if this is true and you do have ions that are able to migrate in the bulk of the material, then they will likely accumulate at the interfaces, create an opposite electric field, thus flattening the band throughout most of the thickness of the material. If at this point we switch the cell to open circuit in the light, then what happens is that you're going to form this wiggly band structure, and the peculiarity of it is that throughout most of the bulk of the device, the electric field is pointing in the wrong direction. That means that if with a pulse of laser we create holes and electrons, the electrons will roll down towards the anode, not the cathode, and the holes will float up towards the cathode and not the anode. And that gives you this negative transient photovoltage, we think. Now, at this point, there's nothing holding the ions at the interfaces anymore, so they can slowly rediffuse back to get a homogeneous distribution, and then you go back to your flat band conditions, and you recover a positive response of the transient photovoltage. So we were quite happy with how we managed to explain this, but just as we were about to publish it, somebody had to spoil it all, making hysteresis-free devices. And the frustrating thing about this is that the material doesn't change. Okay, it's still methyl ammonium lead triiodide, but all that changes are the hole and electron transport materials. And even if you grow the perovskite on exactly the same thing, so P.PSS in this case, and you use a PCBM aluminum cathode or a zinc oxide aluminum cathode, you get a massively different response. No hysteresis in the first case, massive hysteresis in the second. Okay? So what is happening? Well, first of all, let me show you what happens when we use our technique on a device that doesn't exhibit hysteresis. So you can see that the response of the VOC is pretty flat, and you'll notice that all the transient photovoltage spectra are positive. There's no negative component here. So what we think is happening is that we have to consider what happens at the interfaces. All right? So ions will migrate because it's the same material, but something is changing at those interfaces. So imagine a device which doesn't exhibit hysteresis, in which ions are able to migrate, but nothing else is happening. So in that case, at time 0, when we switch on the light at open circuit, you will get this wiggly band configuration. But what will happen is that with your white light, you'll generate a massive amount of charge in the device. All right? And electrons and holes will, if you want, fill up these valleys very quickly, almost instantaneously flattening the bands. So ions are accumulated at the interfaces. They do form this reverse electric field, but we don't see it. Okay? And we can, by making this assumption, we could simulate the band structure of the device. So you have the conduction band up here and valence band down here. And you can see that so the solid lines are at times 0, so when you just switch on the white light, and the dotted lines are when the VOC has stabilized, or after about a minute. And you see that there's not much difference between the two configurations. Also, based on the same assumptions, we could simulate the flat response to the VOC and also the fully positive transient photovoltage spectra. Now, in devices with hysteresis, what we think is happening is that you have recombination at the interfaces of the active material with either a cathode or the anode or both. All right? And this surface recombination helps removing part of that photogenerated charge so that the shape of the band structure is not affected now. So the only way to go back to that flat band configuration is for the ions to rediffuse back in the bulk of the material. Okay? And that takes a little while. And by assuming that, we could show that initially the bands are pointing in the wrong way, and then they flatten out after about 45 seconds to a minute. Again, by just introducing the surface recombination, we could simulate the slow evolution of the VOC. And then we could simulate the negative transient response at early times. All right? Now, how to prove it experimentally was critical. And the idea is that in devices without hysteresis, we think that there's so much photogenerated charge that we don't see the effect. So what if we simulate the VOC by applying a forward bias instead of turning on the light? So now we do the experiment completely in the dark, but at time 0, instead of switching on the light, we just apply a forward bias close to VOC. Okay? And now we measure photocurrent, transient photocurrent, just because it's easier to measure photocurrent when you're applying a bias to the cell. And the signs will be reversed. So now if we do indeed have a reverse electric field in the device, we'll observe a positive transient photocurrent, okay, at early times. So what we do is that we switch the cell to open circuit with this forward bias, and then after a few microseconds we use a pulse and look at the transient response of the current. And in this case, it doesn't matter whether you have a device that has hysteresis or a device that doesn't have hysteresis. You can see that both exhibit a positive transient photocurrent. That means that, at least at early times, in both devices, electrons and holes are moving in the wrong direction. So, to wrap up this part, we think that ions are accumulating at the interfaces with the hole and electron material in methyl ammonium lead iodide perovskite solar cells, regardless of whether they exhibit hysteresis. And you can see here that we could simulate the accumulation of ion density at the interface in both cases. Okay. Now, in the case of devices without hysteresis, we don't include a surface recombination component. In the devices with hysteresis, we do, and that changes completely the voltage response. And surface recombination will also affect the collection efficiency, so it's expected to affect the current voltage scan at all voltages. And so based on that, by having mobile ions in both devices, but in one case switching off the surface recombination and in one case switching it on, we do reproduce this idea, this observation of no hysteresis or hysteresis. Okay, and so the second part of my talk focuses on organic solar cells, right? Specifically, bulk heterojunctions of PCD, TBT, and PC60BM. All right, and this was done mainly in collaboration with Jenny, and the students who have contributed the most were Jason and Beth here. Now, our collaborators in Swansea had really interesting observations on the degradation of the performances of these devices when you expose them to light in air. So what they do is they make the blend film, and then they expose it to illumination, to one sun illumination in air, and afterwards they deposit the contacts and look at the JV response. And they deposit the contact afterwards so that we can exclude the degradation of the contacts themselves in the picture. And you can see that as the time of the exposure time to life increases, the JV curves become worse and worse and worse. Now, interestingly, they could reproduce the same behavior by using a fresh PCD-TBT and blending it with PCBM photodegraded, photooxidized separately. Okay, so you photooxidize PCBM separately, you mix it with PCD-TBT, and you make your blend. And again, the more you oxidize the PCBM, the more you lose performances. And here you have the direct comparison of power conversion efficiencies in both cases versus the amount of oxidized PCBM in the device, measured by mass spectroscopy. So the idea is that in blends where you use polymers that tend to exhibit a fair amount of stability to photooxidation, the fullerene becomes the weak link. Okay? And we wanted to understand exactly what happened in the device in terms of device physics. So the first thing we did was try to figure out the most likely mechanism of photooxidation of the PCBM. Okay, and there's a bunch of publications out there on degradation in solution, as the guys in Swansea did. The most likely of which is the attachment of an oxygen to the fullerene cage to form an epoxide, which then naturally progresses in further oxidation, which is a diol and then a dicarbonyl. Okay, at which point you have an actual hole in the cage. And so what Beth did was simulate the positions, energy levels of HOMO and LUMO in all cases. So on the left you have the fresh PCBM, and then you have PCBM with one epoxide, with a diol, and with two carbonyls. And we focused on epoxide and dicarbonyl mainly because we could measure them directly. Okay, so mass spectrometry showed us that indeed you after photooxidation, you would get the peak for PCBM, but also peaks with 1 oxygen, 2 oxygen, 3 oxygen, and so forth. And then by FDIR, we could detect quite well the formation of additional carbonyls. Okay, so at the beginning, you have a sharp peak, which is the ester on the side chain, and then you get a broadening of this peak with an extra shoulder forming, which is consistent with carbonyls in this sort of environment. So what we did was literally assume that after photooxidation, the acceptor phase would be a mixture of fresh PCBM mostly, and then some epoxide PCBM and some dicarbonyl PCBM. And we think that that would produce a device band structure similar to this, where you have bands coming from the PCBM, and then additional states below the LUMO of the PCBM coming from the oxidized material. And we looked at different techniques to probe that this was actually the case. So first of all, we looked at recombination, all right? And in particular, at charge extraction and transient photovoltaic spectroscopy. So in this case, you would expect that if you have these extra states, they would affect the rate of recombination. Okay? And if you're not familiar with the technique, in the charge extraction, we hold the device under a given white light illumination at open circuit to generate a certain quasi-Fermi level splitting. And then at time 0, we switch the light off and we switch the cell to short circuit to extract all that charge. So we assume that there are no losses. And so if you integrate this transient photocurrent peak, you get the amount of charge in the device under that specific light illumination. For the same light illumination, we measure the lifetime of these charges. So we keep the white light on, and then we use a pulse laser to generate a little bit extra charges, and then look how quickly they decay. And combining this information, we get a picture of what's happening to the recombination. So on the left-hand side, you have charge density versus VOC, or light intensity. They're interchangeable. And essentially what's happening here is that as you increase the amount of oxidized material in the device, you're increasing the amount of charge stored in the device. All right? A way to see it is that if you want to achieve the same VOC, you need to inject more and more charge as the oxidation progresses. And this is easily understood if you take into consideration the shape of the density of states inside the bandgap. Okay, so you just have extra states that you need to fill up to get the same voltage. Now, interestingly, you see that the lifetime of these charges, here plotted versus charge density, increases as well with the oxidation of PCBM. So this means the charges are living longer. Okay? And you can imagine that if you're trapping an electron, for example, near the lumen of the PCBM, that will have a lower likelihood of meeting a hole and recombine compared with the situation in which they're both moving around. Okay? So that's a working hypothesis. So it sounds a little bit counterintuitive that you get higher recombination because you're losing VOC, but you're also getting charges that live longer. But if you calculate the VOC that you would get from the density of charge and the lifetime that you calculated, it actually matches pretty well the voltage that you measure under different light conditions on the same devices. So effectively what's happening is that the effect of extra charge in the device is trumping the effect of a longer lifetime. Another way to look at recombination is using electroluminescence. And now you're injecting hole and electrons and hoping that they will recombine at the interface radiatively, so you can measure the light that comes out. And what we observe is that the electroluminescence, as the oxidation of the PCBM proceeds, seems to shift to red shift, to shift to lower energies. Okay? And this can perhaps be interpreted as the energy of the charge transfer state getting squeezed because of the presence of these extra states below the lumen, right? If some of those states emit light. Now, this is normalized electroluminescence, so if you look at the, so you don't see the change in magnitude. Of course, the magnitude, the intensity of the light that comes out gets smaller and smaller and smaller as you oxidize the material, right? Which is an indication of what's happening to the different recombination mechanisms. Also, if we do electroluminescence on just the PCBM, so no PCD-TBT in this device here, we see not quite a red shift as you oxidize it, but rather perhaps a difference in the oscillation strengths of various transitions. So we're not quite sure yet what's happening in the electroluminescence. But in any case, the ways we explain the effect point to the presence of traps that affect the charge transfer state. just as a control, we did electroluminescence on just PCD-TBT devices, and you see that if you degrade the PCD-TBT, so the polymer, nothing really changes. And the last technique that we used to try to understand these devices is a combination of external quantum efficiency and electroluminescence. Right? So the idea is that you can quantify how much voltage you're losing to radiative recombination and how much voltage you're losing to non-radiative recombination if you can measure the EQE very accurately. So the way it works is that you want to calculate the dark current in the radiative limit, meaning in an ideal device where you only have radiative recombination but you don't have non-radiative recombination. And if you have that, then from the diode equation you can just calculate the VOC that you would have, again, in an ideal device where only radiative recombination was present. The problem is that measuring this dark current is quite challenging. So you can obtain this value by integrating the external quantum efficiency of the device, but you're multiplying it by the black body radiation of the device at its temperature. That means that anything happening at low energies down here is going to have a much higher weight compared to anything that happens at higher energies. So we really need lots and lots of data from down here. So one way to get that data is to use a very sensitive EQE setup that uses a lock-in amplifier, and then use a set of filters to really select the wavelength that you want to use. And that brings us down to about 10 to the minus 5 EQE, where the maximum is 1. But that's not enough. So one thing that we can do is use the electroluminescence itself. So we're looking at a radiative limit, right? So any state that absorbs light will also emit light. So external quantum efficiency and EL quantum efficiency become the same thing, right? So if you get your EL data and you divide it now by the black body radiation, you can get this extension of the EQE down to values of close to 10 to the minus 14. Okay, so now we're in business. Now we can really measure this dark current. And when we calculate the VOCs, we see something very interesting. So here is, for reference, the band gap of the device measured as the onset of the EQE. You have the shock equalizer limit down here, and you have the VOCs in the radiative limit that we're measuring from EL and EQE, as I just showed. So all the voltage loss here in green, that's due to absorption losses. That's because the EQE is not a step function that goes from 0 to 1 at the band gap and stays at 1. But the radiative limit of the VOC doesn't seem to change much when you oxidize PCBM. What does change a lot instead is this orange bit here, which is the difference between the VOC in the radiative limit and the VOC that you actually measure on a solar simulator. So all that orange bit there is voltage loss to non-radiative recombination. Okay? So that points strongly, well, actually tells you exactly how much voltage you're losing from non-radiative recombination when you oxidize the PCBM. And this wraps up the second part of the talk. So I haven't spoken about the transport because we're analyzing the data right now, but we do see a loss in mobility as we oxidize the PCBM, okay, which points again at these trap states for electrons. We did homolume simulations. We saw recombination by transient photovoltage and electroluminescence. And again, we can understand exactly what kind of recombination is going on as you oxidize the PCBM using voltage losses. So I'll just leave it there, and I'll thank all the Nelson Group and all the collaborators in there, and also a bunch of people at Swansea, Valencia, Manchester, and Brian O'Regan in California, who have contributed to the various projects. And also, of course, thank you all for your attention and for having me.
Lots of time for questions.
You have used the EL to analyze the voltage loss. Can we use PL?
The response would be similar. We actually have compared PL and EL, and I do see a similar trend. I think, though, that with electroluminescence, you're probing states that are actually electronically accessible, right? With PL, you may probe states that are optically accessible, but you can't necessarily inject electrons or holes into. So it may give you a skewed answer. But, yes, we have checked that.
Let's thank Andrew once more.
Thanks.